All right. So last time we started learning about how to find what are called Taylor series. And Taylor series kind of look like this. If we have some kind of function, then it's going to be equal to the sum from 0 to infinity of subnumber a sub n times x minus a raised to the nth power. Where remember this a number, this is called the center of the series. Now, many functions can have this representation. This is called a Taylor series. Now, the nice thing about a Taylor series is rather than substituting into the geometric series like before, we can kind of figure these out from scratch for many different functions. The way we did that, the way we find these a sub n, they're going to be the nth derivative at a divided by n factorial. And note that this little exponent in parentheses right here, this isn't the nth power. We're not raising this to a high power. We're taking a lot of derivatives. That's why it's in parentheses right there. So if we take n derivatives, we plug in the center divided by n factorial, we can start getting these a sub n. And remember, the way we usually did that in practice was we started writing these tables, and we tried to see a pattern for these. Now, rather than doing it from scratch every time, like figuring these out from scratch, there are 4 series that appear so often that we often just kind of start from those and then modify those to be whatever series we want. So I call these the big 4 because they show up really often, and there are 4 of them. So the first one, the one we saw first, is the geometric series. So this one is 1 over 1 minus x, and that's the sum from 0 to infinity of x to the n. So if you ever want to make any series for rational functions or things that look like the derivative is in integrals for this, like arctangent or natural log, this is a good place to start from that. Although the limitation here is that our interval of convergence is only going to be -1 to 1, so it's kind of narrow. And then we learned about 3 new series yesterday. So e to the x is a complex function, and for its Taylor series or Maclaurin series, we have x to the n over n factorial. And by the way, a Taylor series is called a Maclaurin series when this a equals 0, or we just have x to a power, then we're not subtracting or adding anything inside there. So we have this is our exponential series, and this has a radius of convergence of all real numbers, and that's what this little fancy r thing in here means. So we can plug in any x we want in there, and it'll still equal e to the x. That's one of them. The third one we have is sine of x. That's the sum from 0 to infinity of -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. You may have learned in either like a trigonometry or algebra class that sine is what is known as an odd function. Meaning if you put a negative sign in there, you can just move the negative sign out of the function. And it's really obvious that it's an odd function here because all of these x's are going to be to odd powers. All these factorials will be to odd powers. That's another reason why sine is an odd function. And in the same way, you probably heard before that cosine is what's known as an even function. So cosine is exactly the same series, only we have x to the 2n divided by 2n factorial. So 2n will always be an even number, so we'll only have even terms and even factorials in cosine. So starting from one of these 4 series, we can get a lot of the series that we're going to use. Now, in the case where we can't get that, then we need to make the table like we did last class by using this formula right here. And I'd be happy to go over that again if some people would like after I'm done talking about this stuff. Okay, so now we're getting pretty good at finding series. We can find series for a lot of different types of functions. So now we're going to start focusing on what we can actually do with these series. I'm going to show you 2 different examples of that. Okay, so here's my first example. So let's remember what the series for arctangent is. Arctangent of x is the sum from 0 to infinity, -1 to the n, x to the 2n plus 1, divided by 2n plus 1. So it's actually very similar to the sine series. It's just that it's not divided by a factorial. It's divided by regular 2n plus 1. All right, now, all right, what are we going to do with this? Well, let's say that I wanted you to find the 99th derivative of arctangent at x equals 0. So this is our function. Let's say I wanted you to take 99 derivatives for some reason and then plug in 0. So how would we do that? Well, if we could have done this in Calc 1 if we had a million years in our hands. We could have just take the derivative of this and then done a bunch of quotient rules on to get out of that. But of course, that's really terrible. We don't want to do it that way. So how are we supposed to do this? Well, we're going to use the fact that this is a Taylor series. So all of these coefficients, -1 to the n over 2n plus 1, remember that these will be equal to, let me just write n for this. There we go. So remember that a sub n is going to be the nth derivative at 0 divided by n factorial. Now, usually we use this formula as written right here. We find the derivatives, we plug in the factorial, and then we get the coefficient. We could also do things the other way around as well. If we multiply the coefficient, which we know, by the n factorial, then we get whatever derivative we have at 0. So we're kind of doing this backwards from the way we usually do it. So in our example, now one thing to be very careful about is that I'm writing this n right here, but what I really mean by this is the number of derivatives. And that also applies for this one right here. Now, it doesn't quite apply for this one. It doesn't apply for a sub n. Well, in order to figure out what this n is going to be, we need to figure out what power, or what n makes the power of x match up to the one we want to be. So in our case, we want 2n plus 1 to be 99, because we're trying to get the coefficient that's next to x to the 99. So 2n plus 1 is 99, so 2n is 98, n is going to be 49. So what we do is we take this n and put it in to here. So I have -1 to the 49th divided by 2 times 49 plus 1. So this is my a sub n right here. Then I have the factorial. But remember, the factorial is going to be based on the number of derivatives, not on the n value. So I'm going to multiply by 99 factorial, and this will be my 99th derivative at 0. So these two numbers right here, the number of derivatives and the factorial we multiply by, those will always be the same. It's just that this n might be different. So there we go. So this crazy number right here is going to be our 99th derivative of 0, and we did that faster than we can maybe even do 3 derivatives of this, let alone 99. So if we know the series for a function, we could easily compute the higher derivatives for it as well. All right, so that's my first example on what we can do in this. Our next example has something to do with limits. So let's say that we had to compute this limit. So the limit as x goes to 0 of sine of x minus x plus x cubed over 6 divided by x to the 5th. Now you might be like, oh, well, okay, I could just use L'Hopital's rule on this because this will be 0 over 0. And you are right. You definitely can use L'Hopital's rule on this. But as we've seen before, sometimes you need to use L'Hopital's rule more than once. How many times do we need to use it here? Well, since we have an x to the 5th down there, we need to use it 5 times, which that can get kind of annoying. And there have been problems like this where you have to do it like 16 times or 100 times. So that's definitely not going to be good. The power of x up here, it's going to be 3. There we go. X cubed over 6. All right. So what are we supposed to do? Well, we're doing stuff with series. So why don't we try to replace sine of x with its series and see what happens? Okay. Well, remember the series for sine of x, that's the one with all the odd terms. And -1 to the n, x to the 2n plus 1 divided by that factorial. And then we have these two terms right here. and then all of that is divided by x. Okay, well, I just looked like it made everything a lot messier, right? Because we have this nasty sigma notation in there. But if we write out the first few terms of this, I think we'll see something interesting happen. So the next thing I would do is I'm going to start plugging in n values to this so I could write out the first few terms. So if I put n equals 0 into here, this will be -1 to the 0, which is 1. This will be x to the first power divided by 1. So I have x. If I plug in 1 here, I'll have a negative x cubed over 3 factorial. And then let me do 2 more here. X to the 5th over 5 factorial minus x to the 7th over 7 factorial. And at that point, it would kind of just keep going on. I don't think we're going to need more terms than that. And then I'm going to take away x, and then I have this x cubed kind of crammed in the corner. And remember, all of this stuff was divided by x to the 5th. Okay, so now we look at this, and then something interesting happens. So I have this x in the front, right? And then I have a negative x back there, so those can cancel out. And in the same way, this negative x cubed over 3 factorial, well, 3 factorial is 6. So this and that will cancel out. Now, it doesn't seem like I have anything left to cancel these guys, but the good news is that now all of my powers of x are at least 5. So I can safely divide by that x to the 5th down here. So I can cancel that with this entirely and leave a 1. This will only partially cancel, and I'll have an x squared left up there. And then I would have like x to the 4th for the next one if I decide to write that. All right, so let me write out, without all this crossing out, what we have. So now that we've canceled a ton of stuff, we have the limit as x goes to 0. Now this is just 1 over 5 factorial minus x squared over 7 factorial. I'll write the next one. X to the 4th over 9 factorial. And then that would go on forever. Now, if I do the limit as x goes to 0, this is unaffected because it doesn't have any x's in it. Meanwhile, these guys right here, they do have an x. So all of these will go to 0. And along with the rest of the terms over there. So I just end up with 1 over 5 factorial or 1 over 120. Now, in this case, I was kind of going through it slowly, and I didn't need to do that many L'Hopital's rules. So it may have actually taken about the same amount of time to do L'Hopital's rule here. But it will definitely save you a bunch of time in the future when you need to do even more derivatives. Let's see here. Why did it turn into x squared? Well, originally it was x to the 7th down here, but then I divided it by an x to the 5th. So we had an x squared left over. And that's why this was normally an x to the 9th, but I divide by x to the 5th. So now it's x to the 4th. So I just kind of cut down all the powers of x by 5. All right, so anyway, so that's kind of a quicker way of doing limits by using the series. Let's see, what happened to the 3 and 6 factorial? Well, this series doesn't, let's see here. Well, the 3 factorial right here, that canceled out with this one right there, because 3 factorial was 6, this was positive, and that was negative. And this 6 wasn't a factorial, by the way, this is just a regular 6, which is equal to 3 factorial here. So how could I eliminate x squared to the 7 factorial? Remember, I'm taking the limit as x goes to 0. So if I have any x's left over at all, those are just going to head to 0. So the only one that didn't have x's left over, because it perfectly canceled, was this 1 over 5 factorial. All right. So that about does it for my intro. So as I said before, let me know if you have any questions on either Power Series 4 or Power Series 5. I'd be happy to help you out.